Hello, this is Dr. Heidelberg, and our presentation today is signals in mechatronics. We'll follow the textbooks by Bolton, and the module 2 covers signal conditioning and digital signals. The signal conditioning refers to converting signals format, such as light sensor to voltage or heat to current. It also deals with amplification of signals, such as moving enough power to operate a solenoid. Noise filtration, which may be induced into our signals from vibration, EMI, and radio frequency interference, and also mathematical formulation, such as linearizing nonlinear data. The signal conditioning refers to protection of the device when the sensor signal is sent to a measuring device or to the cloud. One way of dividing the signal is by using a resistor, such as we see over here, together with another resistor. The two will divide the reference voltage into a fraction, which is determined by the formulation V out equals to V in times the resistance across V out and divided by the sum of the two resistances. The resistors, as we'll be using in a lab, will be designated by the color code. The color code will be given to us in the lab material. What we see over here, that is an example, the 6-band, 1, 2, 3, 4, 5, 6 example. There could be also 5-band and 4-band notation, but in this particular example, red designate the first digit as 2, the second digit is 7, violet, and the fourth digit is yellow, which is 4, and then the black digit, which is the fourth one, which is 1, is indicating the multiplier, which is over here times, basically this is the 0, which is multiplying the 274 by 1. We also have here a designation of the tolerance and the temperature coefficient. One of the components that we'll see later on is a diode. The diode is an electric component that is built from ceramics, which is actually doped with holes such as the positive edge of it, and with electrons, which is the negative edge. And then the signal is being amplified, as we see over here, when the polarity is charging the negative with a negative charge. So the electron will then move in a counterclockwise direction, and the current, by definition, will move in a positive direction. If we try to move the current in the other direction, the polarity will reverse. Then it will current will be blocked. That is, this spark current will not go from this side to this side unless we are exceeding the breakdown threshold, in which we will burn out the diode. A similar diode is the Zener diode, which is pretty similar, but instead of having a breakdown here, the Zener diode will have a similar experienced a relationship. On a positive side, when it passes the reverse bias, it will have a negative side. So this helps to maintain a steady voltage over a load, such that if we pass it, the load is going to be steady. The notation of a Zener diode is with the cathode marked with a black sign, and the anode is the free one. The operational amplifier, a very common device. We see here as an example. And what it does, it amplifies input currents and voltages that are coming into its input position over here, the terminal, and the output is determined by the negative of the input times the feedback resistance divided by the input resistance. So this is the amplification. So if we have a large value of RF and smaller value of R1, then the amplification will be accordingly. We have another configuration for the operational amplifier is an integrator. If we put the capacitor on a feedback loop, we will actually charge it, and the voltage is going to increase in time, as shown over here by the formulation, which is the V out equals to the integral of V in dt, and the coefficient that preceded is 1 over RC. So in other words, the voltage at time t2 minus the voltage at time t1 will be the integral of this expression between time t1 and t2. The principle of the transistor, which is a combination of an element that transmits the signals as well as resistor signals, is shown over here. We have a semiconductor device with one side is doped with electron, the other side is doped in electron, as this is an NPN device, with the center is doped with holes. And the designation of NPN is shown over here. We have the emitter. That's where the electrons are being emitted to the collector. And then we have a base. So if we have, for example, over here, we see a circuit diagram. We have a voltage between the collector and the emitter. And that voltage cannot be transmitted unless the base is providing some voltage to let the electrons which come in from the base join the electrons that come in from the emitter and go into the collector. So what we see here is that is the base current that is provided by VCE. This is the base current, which is the VBE. And the one alone is not going to conduct, but when we provide in a small amount of current into the mainstream, then a conduction is going to take place. So if there is a voltage over here at the collector and there is no base current voltage, there will be no conductivity. But with a small amount of base potential, then the current is going to flow, and while it's flowing, it could activate various actuators. We see here another example. We'll see in a lab the transistors with the collector, base, and emitter pins. We also over here see the 1, 2, and 3 as shown over here, which one is which. And over here we see the, again, the diagram that shows that we could activate the output, whatever device we have over here, by providing a V input and activating the voltage between B and E. When we do this, then the current is going to flow, and we're going to have a V out over here to do the work we intended to do. And we also have an optical isolators with a diode. We have the diode, the LED, that light emitting diode that provide infrared light into a phototransistor. And the phototransistor is actually generating with the light the flow of electrons into the base, and then electrons will be going from the emitter to the collector, and the current is going to go through the transistor. We see over here an example of a Wheatstone bridge. This is a device that could be used to measure resistance of various elements with unknown resistance. We may have here a R1, R3, and R2 as known resistors. With R2 could have a varying resistance. And then we have an unknown Rx. Now, if we make the voltage flow in VG to be 0 by adjusting R2, then, as we see earlier, we have a ratio that the voltage drop between these 2 points is equal to the current flowing times this resistance. And we could see that here that the ratio of R2 divided by R1 has to be equal to Rx divided by R3. So if we know R2, R1, and R3, we can calculate the Rx. We can also use this as a strain gauge measurements of stresses, and putting a strain gauge right in here where the resistance will change with strain and stress. And then the voltage change, which we could measure, will be proportional to the resistance changed over here. To calculate the resistance, the current and the voltage drops in a complex circuit, we use the Kirchhoff laws, and we could click on this YouTube device, and this gentleman provides us a nice lecture how to do that. In principle, we take the circuit diagram and we sum up all the currents which are flowing into a node. We write I1 equals I2 plus I3, and then we write the voltage across each loop. We sum up all the sources must be equal to the elements that receive the power, and then we have a few equations and few unknown depending how many loops we have, and then we can use a matrix algebra tool in order to solve for the unknown I2 and I3. So with this we can move on to filtering. We see that with the combination of a resistor and a capacitor in series, we could receive a signal across the capacitor, which behaves as a filtered signal. So if we have a sine wave over here, the signal may have many frequencies, and this combination is going to reduce the amplitude of the output. The input is going to be the input is going to be given to us, but the output is going to have an amplitude at the frequency which we isolate at the same frequency, but it's going to have a gain, and the gain is going to be the ratio of the output divided by the input magnitude. We see it over here, and the filtering, this is a low-pass filter, showing us that as we increase the frequency, the gain is decreasing. In other words, the output gain is going to be lower at higher frequencies. So this is a low-pass filter. And we can have a high-pass filter, which does pretty much the opposite with the capacitor in series with the resistor. Here we see an example of so-called pulse width modulation, which is very common in mechatronics, amplifiers, and driving motors using pulse width modulation. Many times we see here a device, and the principle here is that we let the pulse be extended a certain period of time, and then we shut it off. So it's on, off, and every time we put it on, it takes the magnitude of the function that we see over here and increase it by a small amount, and then it holds, increase it again, and then it holds, and then a smaller amount, and then it holds, and then it reduces by a small amount because the pulse is a lower duration, holds it, and this way the pulse width modulation could track an analog signal. We see over here an example of a device which is being used in digital signal handling. This is a Schmitt trigger, and what we see here is an example that we have the Schmitt trigger, which has a performance such as we see here. We see the hysteresis. As we come in between here, there is no changes in the signal. As we go beyond it, then we get a positive, and the positive stays until we cross in a negative direction, and then it becomes negative. So we see over here an example how it could be used. We have over here a switching device, could be a clock, and we have over here a capacitor. So we have over here a 5-volt supply, and then we have the Schmitt trigger. So when the switch is open, then what we have is we are charging the capacitor, and then as we charge the capacitor, the voltage is going to increase, and we get a value of 1, okay, at the saturation. And then when the switch closes, then the voltage is going to drain into the ground, and this immediately is going to become a 0, and then the output is going to be 0. So that's the way we can use it in switching. We have here another device, which is a comparator that checks a given input versus a reference. So when the given input is equal to the reference, we want a value of 1. And when the input is less, then we want a value of 0. This is bits of 1 and 0 that will tell us if we are at the same value. So if V0 is less than V reference, we're going to actually have a negative is going to be the dominating voltage, and then the output is going to be 0. And when V is going to be higher than this, the sum of them is going to be positive, and then the output is going to be 1. We see here using the Schmidt trigger, the integrator, and the comparator, how we can use a circuit to generate a pulse width modulation. We have the Schmidt trigger that generates here a square wave at certain intervals. We have an integrator that takes the square wave and integrate that and get a triangular wave. And over here we have the comparator that can actually shut off or turn on the signal depending on what is the input function that we feed in. The example over here shows us how we can take an analog signal and change it to a digital signal such that we could send it through the buses. So we see over here again a Schmidt device that helps us to maintain a constant reference signal, which we put over here. We have the sample and hold device that allows us to charge the capacitor, and then every time we charge a capacitor, we increase the value in increments, and then we see that each one of each element will have a binary digit that we can transmit through the buses. Binary digits are combined of a series of zeros and ones, and they are used for data, address, commands, and the entire computer and controller operation is done in binary digits. Now, this is an example of 8-bit, which is called a byte or an octet. And this left one is the most significant bit, and the right one is the least significant bit. Now, to change a number like this into a decimal notation, base of 10, what we do is we take the first number, which is 0, and multiply it times 2 to the power of 0. Then we take the second one, 0, times 2 to the power of 1. Then we take the third one, which is 1, and we multiply times 2 to the power of 2. And so on and so forth. As we go each time, we take the coefficient 0, 1, and multiply times the 2 to the power of that position. And in this particular case, we get 156. How do we add these binary digits as a controller does? We have an example over here of 101 in binary notation, which is 5 on a basis of 10 scale. And then we have 111, which is 7. So we take 1 and 1 is 0. And now we have to add a 1. So 1 and 1 is 0. And now we have to add a 1. So 1 and 1 is 0, plus we have to add 1 is 1, and then we have to carry over 1. So the total is 1100. and this is equal, according to this formulation, to 12. Now, the bits per second that the network that we're working with, or protocol that we're using in a control system, is depending, for example, on the wireless programs, is like we have in the 3G, 4G, 5G, is given to us here below. 3G is 384 kilobits per second. The 4G is 100 megabits per second, and the 5G is 10 gigabit per second. Now, what is a kilobit, megabit, gigabit, and terabit? Over here, we're giving it as byte. So kilo is to the kilobits is 2 to the 10 is 1,000, a factor of 1,000. Megabit is 2 to the 20, which is a million. Gigabit is 2 to the 30, and this is a billion. And terabit is, of course, 1,000 times more. The similar notation is called the hexadecimal, and it has 16 different values. We have going up to 9. This is going to number 9. And then we have 10 of them, including the 0. And then we have A, B, C, D, E, F, which account for 6 more, taking us all the way to 15. So altogether, we have 16 different values. How do we convert the hexadecimal to base of 10? We take, as an example over here, this is D1CE. So E is 14. So we see over here 14. So we multiply times 16 to the power of 0, which is 1. So we are left with 14. 12 is 12 times 16 to the power of 1, which is 16. Total is 192. 1 is multiplied times 16 to the power of 2, which is 256. And 13 is multiplied times 16 to the power of 3, which is 53,248. The total sum in decimal is 53,710. So this D1CE, this is equivalent. So you see that less values can define higher numbers in digits. When a computer reads through the compiler the notation of 0 cross, and that value, it recognizes this as a hexadecimal number. We use ADC, analog digital converters, to take from sensors like a thermal sensor, the analog signal of temperature, and convert it to a digital signal on the way out. So here's an example of Texas Instruments, and this, by the way, all of these figures are referenced over here at the bottom, in case you like to take a look at greater detail. We see over here the example. This is a linear function of temperature as a function of the voltage output. If we put different resistances, we may get a nonlinear configuration. So this is going to be digitized into the controller for further process. We see here an example of how analog to digital converter may work. We have here a clock, and when we have a command that comes here to an AND gate. We'll see next time some logic circuits, and for now, the AND gate takes a signal from one terminal and looks at the signal in the other terminal. And if both of them are 1, then it gives an output of 1. Otherwise, it will be 0. So what we do here is we have a voltage input that we want to digitize, to take it from analog, to convert it to digital. And then we have a comparator here that compares another signal that comes into this amplifier. And only when this signal is the same do we get a 1. So when we get a 1 at the AND gate, and the signal over here is identical to V in, we get another 1, then we come in and we increase the counter. Now, the counter has a digital output for in several bits, and these bits actually describe the current digital value of the input. So we take that current and we convert it back from digital to analog, and we put here the analog conversion. And we continuously doing it until we reach a value over here, which is identical to the value that we put in. And this is the digital output of that input. So this is one example. There are many others that convert analog to digital number. We see here an example of a sampling of an analog function. And the question is, at which frequency should we sample and hold? There is a theory, Nyquist theory, that says that the frequency at which we should sample should be at least twice the highest frequency that we want to measure. Otherwise, we're going to get aliasing, and this is not going to provide us the correct view of the input function. For example, you see over here that the frequency of sampling is much higher. We have 1 sine, okay? This is the frequency of the input. And we have over here sampling of 1, 2, 3, 4, 5, many, about 10 times more. Over here, we have a little bit less, but it's still tracing the input. And over here, we have twice as much, okay, which is over here, frequency of 1, over here, frequency of 2, okay? And then we see that we still can trace the function. We see over here, again, sample and hold device, where we have an ideal sampler over here with the capacitor, and then we could hold it and get the analog input converted into digital input. The data is, and the clock are being sent to the devices from a micro controller through buses. We see over here an inter-integrated circuit, which is I2C, so-called protocol, where we can use 2 wires in order to communicate data and clocks from the master to slaves. Slave could be analog to digital, digital to analog could be another slave. And we see also over here that these devices have the so-called pull-up resistor. Now, what is the pull-out resistor? We see an example over here. If we have, for example, a logic gate over here, and we have an output, and we have an input over here, what we like to do is we like to assure that the input, which is typically 5 volt to 3 volts, this is the to designate 1, and 0 to designate the ground. So when we have the resistor over here, then when we close the switch, then the voltage over here is 0. We assure that the voltage over here is 0 because it goes right to the ground. And when we open the switch, we assure that the voltage over here is going to be 5. So this gives us a better control of the values of zeros and 1, and less actually affect by the surrounding noise. Now, the transmission of signals through the cables from the host computer all the way to the device that we like to sense the data from, or to the actuator where we like to sense it, is done through various networks. Here are the specification, for example, of fast Ethernet. We see the frame structure that includes various components, and the definitions over here is how many bits and bytes each one of these elements contain. Now, the whole process of communication goes all the way from the application where the data that has to be sent is being generated to the transport, which send a segment, including the transmission control protocol that allows it to be routed to the right destination, and then going to the network, which actually adds the IP address and makes it then a packet. And then it goes into the lower layer, the data link, which is added into the packet to make it a frame, all the way to the wires or the wireless communication to the destination address. So we'll see more in upcoming sessions. We also saw a little bit of that in the orientation, and what we should realize that we as mechanical engineers are not expert in IT, and we could certainly consult with them, but we could take a look at the details of each one of them and actually Google what the MAC is. We may not know it as mechanical engineer. This is media access control, and we can see the details, how it's been presented. Here's an example of one acted that is the start frame delimiter. And again, all these definitions may not mean to us quite a lot as a mechanical engineer who use this in application, but it's important to become familiar with the notation. We'll see a lot segments and packets and frames, and we like to know what they stand for. The cabling for the various communication devices are also specified in data sheets with pinouts. We could get the course when we do some sizing for components, for sensors and elements that we need to control. And there are quite a few of them. Some of them are moving. Some of them have to be shielded. Some of them combine both mechanical elements such as air as well as electrical signals. So we should, as mechatronics engineers, be familiar with the cabling and the connectors that make the physical layer of the communication system. Here's an example of a multiplexer. Once we get familiar with some of the components, it starts making sense when we see circuit diagrams like this. A multiplexer will take in several signals from several sensors, and they all will come in here, and only one of them will go out. How will one of them will go out? It will go out when we make a selection. So we could select, we have 4 of them, and we have 2 selections. So we can have 4 options. This could be 1 and 1. This could be 1 and 0. This could be 0 and 1, and 0 and 0. So for example, let's see what happens if this signal is 1, okay, and we have this signal is 1, then this is an AND gate, this will be 1, and then this signal is going to be out, and so on and so forth. So these are the so-called multiplexer. Now, when we transfer data in the physical layer, we will see that many protocols have a parity bit and also sum check. Parity bit will make sure that we have we add a one bit such that we could count the number of ones and 0 in the data stream. Sum check will take several bytes or several octets that are being added together to make sure that the sum at the transmission equals to the sum at the receiving. Here's an example of a data transmission with sum check. We have here an IP header with a source address, IP source address. Here we have the numbers 146, 149, 186, and 20. And then we have destination, another number. All these values are written in hexadecimal. And what we like to see here is how the sum check is being done. So for example, we take over here a 4 bits and we add it to the next 4 bits, and 0 and C is C, 0 and 6 is 6, 5 and 0 is 5, and 4 is 4. That was easy. But then we take the next one, 92CC, and we add it to this sum, okay, in the process of getting to the bottom line. So here we have 456C plus 92CC. So the way we add that is we can convert that to the decimals here. We have C, and we have C is 12 times 16 to the power of 0, 6 times 16 to the power of 1, 5 times 16 to the power of 2, 4 times 16 to the power of 3. And similar, we have 12 times 16 to the 0 for the second one, and then we add them up. So when we add them up, we have 12 and 12 is 24. So this is 8, and then we have a carryover of 16, which we bring over here. Then we have 6 and 12 is 18, plus 1 carryover is 19, and that means that we have 3 plus a carryover of 16, and together they'll make 19. Now we have 5 and 2. So this is 7 and 1, and that means that we have 8 here, and there's no carryover. And here we have 4 and 13 is D. So the result is D838, as we see it over here. So that's an example of a checksum as done on protocols and a way how we add up hexadecimal. This shows us digital signal processing example where we see over here that a device such as a recording device is sending signals through wireless into an ADC converter. The digital numbers come into the digital signal processor, which operates mathematically on it, filters it, and that it may go into memory. And on the way back, the device sends the digital signal to the digital analog converter and can actuate the actuator on the other end of the system. So this completes our presentation, and we'll talk more about the logics on our next scheduled